Welcome to our presentation on the topic of using time series clustering to examine the presence of decrement in Parkinson's finger-tapping bradykinesia. Parkinson's disease is a progressive neurological condition. It's the disease that has afflicted the late Muhammad Ali and Back to the Future's Michael J. Fox, and if you've seen videos of them, you may recognise the presence of tremor. Although this is the most commonly recognised sign of Parkinson's, a range of other clinical signs may also be present, and of these signs, bradykinesia is the key feature of Parkinson's. It must be present in addition to tremor or rigidity for Parkinson's diagnosis to be considered. Well, what is it? Bradykinesia is simply slowness of movement. The presence of bradykinesia is commonly assessed using a finger tapping test. During the test, a patient is asked by the doctor to tap their thumb and forefinger together as large and as fast as possible. They do this for around 10 seconds, and the doctor rates the amount of bradykinesia. There are two standard scales for this, but we consider just one here, called the Modified Bradykinesia Rating Scale, or MBRS. In this scale, bradykinesia is graded from 0 to 4. 0 if a patient has no bradykinesia, and a 4 if they have very severe movement problems. The video playing now shows an example of a normal test in which the patient is not displaying any signs of bradykinesia. Clinicians are taught to look for bradykinesia by seeing if the rhythm of tapping changes, if the amplitude of the finger tapping changes, and if there are hesitations in movement. And in previous work, we showed that we can automatically classify a video recording of finger tapping tests into a UPDRS bradykinesia score. Here, we are interested in something slightly different. In the clinical literature, finger tap amplitude typically decreases during the test for someone showing bradykinesia. This is a concept known as decrement. Our clinical colleagues hypothesised that some patients show signs of a second wind where the amplitude may increase after an initial decrease. If this were true, then clinicians would need to think more carefully about how to assess bradykinesia. The goal here then was to provide evidence for or against the idea of a second wind or a non-linear decrement. The data set we used for this task was a set of 1D signals derived from 137 finger tapping videos. These videos were recorded from both Parkinson's patients and normal controls who did a finger tapping test. We recorded the test using an iPhone at 60 frames per second. Each video was trimmed to 11 seconds. Conditions were not strictly controlled, though the phone was at around 1 metre away from the patient. From the video, clinical experts rated the test using the MBRS scale from 0 to 4. We then extracted the pixel coordinate of the thumb and forefinger at each frame of a video using Deep Lab Cut, a ResNet trained for pose estimation. The distance between the two coordinates were used to create a 1D time series, of which an example is shown here. And of course, the coordinate extraction was imperfect, so we filtered the resulting signal. To get an idea of the decrement, that is, the change in thumb-forefinger amplitude over time, we extracted the upper envelope of the time series. We did this simply by extracting the local maxima using MATLAB's inbuilt function, and then using cubic splines to join the dots smoothly. Finally, we normalised the envelopes via a Z-score transformation. To determine whether the second wind effect was a common phenomenon, we sought to categorise these time series envelopes. To do this, we needed a way to cluster these time series, and we used two approaches to cluster them. First, a simple k-means in which the similarity of signals is measured using the straight line or Euclidean distance. Here this means comparing the amplitude of the signal at each frame and calculating the root mean square difference. We can then apply a standard k-means to assign signals into clusters and use the cluster centre to provide an archetypal example of each cluster. The main problem with this approach is that it does not preserve shape. So consider a bunch of signals that end up being in the same cluster. They all have the same shape but are offset in time. Now the corresponding k-means cluster centre is the equivalent of taking the arithmetic mean of these signals, and this has the effect of averaging out any local structure. In our synthetic example, this is shown on the right in red. An alternative approach is to use dynamic time warping rather than Euclidean distance. In dynamic time warping, two time series are also compared, but we warp one in a non-linear manner. The amount of warping required to produce a match provides a measure of a similarity between the two signals. To avoid the problem we just highlighted, we have to adapt k-means to produce meaningful cluster centres that preserve that local structure. To do this, we use dynamic time warping barycenter averaging, which is an iterative method for estimating a cluster centre, initially proposed by Petitjean. For both standard k-means and the dynamic time warping equivalent, we assumed a priori the presence of 5 clusters corresponding to the 5 categories in the MBRS score. To recap, here is the analysis and overview showing how we go from raw video to a 1D signal to the extracted time series envelope, and then finally clustering the envelopes. Here are the results of the two methods, where the red lines represent the cluster centre, archetypal envelopes. The contributing envelope time series are shown in grey, and the cluster centres are in no particular order. For both methods, we see instances in which the envelopes appear to have a rapid ascent or descent at the start or end of the time series. Looking back at the original waveforms, we have observed that these do not reflect reality, but instead are a limitation of the envelope interpolation. I mention this here to help with the interpretation of the envelopes going forwards. For both standard k-means and the time warping equivalent, we see a cluster centre in which the amplitude is almost unchanging throughout. As expected, the envelope corresponding to standard k-means is smoother than the time warping clustering. When we examine the constituent time series, in both cases, the clusters primarily represented are those who had no bradykinesia, a score of 0. For both methods, we also see a cluster centre in which there is gradual decline in amplitude over time. Both of these clusters were associated with participants who had been rated with more severe bradykinesia. Importantly, none of the clusters show any indication of this second wave non-linear decrement. In all cases, the amplitude either remains constant or decreases linearly over time. In conclusion, the analysis here answers an important clinical query about whether bradykinesia decrement is sometimes nonlinear. From our time series cluster analysis, we found no evidence to support this hypothesis. We used a pair of methods to ensure that clusters were truly representative of the underlying envelope signal, and in doing so, we confirm the validity of the existing clinical approach. We also lend credibility to other automated approaches for assessing decrement, which have all assumed a linear decrease in amplitude. This work is part of an existing project collaboration with investigators from the University of Manchester, Leeds, Loughborough and Tasmania. Our special thanks go to Zhe Binzhao, who conducted the bulk of this analysis. Thank you.